Welcome back to our course on measure theory for probabilists. Last time we introduced sigma algebras on product spaces, and this time we will make use of this by studying measures and integrals on product spaces. There we will meet Fubini's theorem, which allows you to compute integrals with respect to product measures. And we will also learn about convolutions of measures. So let's get started. So we are dealing with measures on product spaces. And today these will only be finite products. So for example, let's just take two measurable spaces. And let's define something. First of all, we need a measure on the product. And usually what you're doing is you're doing this by a so-called transition kernel from one space to the other. What's this? So let me draw a picture. Omega 1 is here. Oops. Omega 1 is here. Omega 2 is here. I would like to define a measure somewhere on the product. And what I'm going to do instead is for every omega 1 in omega 1, I will define a measure on this slice here. So that's the slice omega 1 times capital omega 2. And I'm doing this by a so-called transition kernel, kappa of omega 1, let's call it d omega 2. So if I am in omega 1, what's the distribution to be somewhere on the omega 2 axis? So, and this function kappa here is called a transition kernel. And if the first coordinate here is fixed, it's a measure on the second kernel. So for all omega 1 and omega 1, this map in the second coordinate is a measure on F2, so on the second space here. And there's something else I need to make sure of. If I fix, let's say, A2 in omega 2, then I also have the map for fixed omega 2 in the first coordinate, and that has to be measurable. We're going to need this when it comes to integration. So this is a transition kernel. I will also make an example soon on the next slide where I will link this to Markov chains. But that's just on the next slide. So, okay, sigma finite kernels are defined as sigma finite measures. And the special case is a stochastic kernel. And the idea is that this measure here is a probability measure. So for each omega 1, it's a probability measure in omega 2. So what does this have to do with Markov chains? Remember, in Markov chains, you have something like a matrix P, Pij, I and j ranging in something. And let's say P11, Pij, and so on, filled with all these entries. And what was this? Pij is the probability if I'm in I currently to move to j. And that's similar to what we had here, because in the transition kernel, kappa of omega 1 d omega 2 is the probability if I'm in omega 1 right now. What's the probability to be somewhere in omega 2 in the other coordinate? And here it's just called ij, but in principle that's just the same. So from such an Pij, I can formally also define such a transition kernel, and that would be this here, kappa omega I. So I is fixed, so that's the row in the matrix, which is fixed. And then I have the distribution over all the entries you have here. So Pij, or j ranging where it is, from 1 to n, for example. And delta omega j is wrong, that should be delta j. So that's the point measure on the jth coordinate. And that's now a Markov kernel from omega to omega. So that's a connection here. And as you know, these Markov chains, they're built from these stochastic matrices. And they're called homogeneous if they stay the same in all steps and so on. So that's a connection to something which you already might know. Then let's come to the next topic, which is measurability. So in this talk, I'm not going to show you the proofs. You can read them in the manuscript. They're just technical. I want to focus here on telling you about the concepts. So I have a transition kernel here. I have a function here. That function goes from the product to R plus. And I would like to define something like an integral. That function here is measurable. And first of all, in order to come any further, I need it for fixed omega 1. So this here is fixed in the whole thing. I view this here as a function in the second coordinate. And I integrate over this. So that's something you know what that is. Just omega 1 is fixed. And as a function in omega 1, it is f1 measurable. If f was measurable. Okay. Measurability is usually not such a big problem, but you have to check it. And the second is, I can define using some mu, which is a sigma finite measure on, okay, that's f1 here. That's on f1. That's a transition kernel from f1 to f2. And this cross is here then a measure on the product space, which means I also have to put in a product here. And what is it? Well, okay, we saw that this here is a function in omega 1, and in this function it's measurable. So as a function in omega 1, I can integrate over some mu. And when I do this, I obtain a measure. So I plug in a product and I get out a value. And this is then here this sigma finite measure on omega 1 times omega 2. That's something we are going to need in what is called Fubini's theorem. Fubini's theorem makes a connection between two things. First, integrals with respect to this product measure. So, no, sorry, not the product measure, the measure on the product. And second, well, here we had something which we already had in this slide here. And you can integrate now over mu 1, over omega 1. And it's claimed here that these two things are the same. So on the left-hand side, you have the usual definition, some function integrated with respect to some measure. And on the right-hand side, you're doing this iteratively. Here you integrate over the second coordinate, and then you integrate also over the first coordinate. And these two things are the same, provided that f goes to R plus. Usually you write it like this here. F goes to R plus. Or it goes to R, and you know that the absolute value is finite here. So that's Fubini's theorem. And one corollary is, okay, here I said that here is a measure on the product space. And a product measure, which is something different, that's, so to speak, if this kappa does not depend on its first coordinate. So in this picture from before, no matter where you are, the distribution where you land on omega 2 is always the same, no matter what omega 1 is. So we will later also say omega 1 and omega 2 are independent. Yes, so if kappa has the property that kappa does not depend on omega 1, then you can define the product measure just like this here. So, yeah. And what we also have, if f goes to r plus, the value of the integral does not depend on the order of integration. So here you could also play the other game. Here measure in omega 2 and omega 1 is the same as integrated over the second coordinate, and then you have a measure on the first. And when you're doing this, you have here a product measure. So the measure on the product of a product set is the product of the values of the measures. Okay, let's make an example. And the definition comes on the next slide, I guess. Let's take d-dimensional Lebesgue measure. For example, d equals 2. And let's take this function here. Let's look at this. So, when, for example, x is fixed, if x is fixed, you have a function y here, you have its square down here, and you square this. So that means that, let's say x is fixed, x is 0, and 1 over y to the 3 is integrable. At 0. No, wait a moment. No, it's not integrable in 0, but that's not the case. That's not the point. You always have here this relationship. F of x and y is minus f of x and minus y. So if you fix x here, and if you integrate over this, you will also always end up having 0 here. Okay, if except x is 0, then it's a bit tricky because you have something which is not integrable. But x being 0 is a very small set itself. So this one here is always 0. And that means you can also integrate this here over x. And you still get 0, because the integral over 0 is 0. So why is that? So that's the case here because of the symmetry here. However, the absolute value of f is not integrable because the same trick doesn't hold. So this here does not hold. Yeah, so here, if you fix x, you integrate over y, So y equals 0 is a very special point. But for the absolute value of f, y equals, y is not that special. Because if you have here the absolute values, you no longer have the symmetry, and you have to come up with other ideas if that's integrable or not. And it's not integrable, and the reason is, well, near 0, I have something like 0, 0 here, and 0 also there, but to the power of, well, 4 essentially, and here to the power of 2. 1 over something squared is not integrable on R2, or absolute value is not integrable, because f has a non-integral pole at the origin. So that means here it can happen that this iterated integral, like this here, exists and equals 0, but the function f here is not integrable at all. Yeah, that's what can happen here in this example. Okay, so much for this. And now we're going to talk about an application, which are convolutions of measures. So in simple terms, the convolution of two measures is the image measure of mu and mu1 and mu2 under the addition. So what does this mean? So mu1 star mu2 of some a, that's mu1 cross mu2. So now we'll measure everything. S to the power of minus 1 of a. So you make the pre-image of a under the addition, which means if one is x1, the other one must be something in a minus x1. Then you can compute this convolution. Let's make an example. I have two Poisson distributions, and I want to compute the convolution. Convolution here means, okay, I forgot something like k here, so that's the value at k. I have to make up here in my mind what could this and this here be, such that their sum is k. So m is the first, n is the second, and the sum should be k. And then I also have the weights of the two Poisson distributions, e to the minus gamma 1, gamma 1 to the m factorial, and the same for gamma 2. And that's the basic formula, what the convolution looks like. Yeah, I can compute this a bit differently. So if m plus n equals k, then n must be k minus m. Just write this. So n is k minus m. Yeah. And now I can compute further. First of all, put everything out of the sum here, which does not depend on m, which is this here. I also have a k factorial here, which I correct immediately by a k factorial here, and I divide by m factorial times k minus m factorial, and that's the same as here. And this sum here is something you might know, because that's the binomial theorem. M choose k times gamma 1 to the power of m times gamma 2 to the power of k minus m, which is then gamma 1 plus gamma 2 to the power of k, which is exactly this denominator, which means this term here cancels completely, and I end up with all the rest, and these are the possible processes with gamma 1 plus gamma 2. That was the first example, and the second one is with normal distributions. I have two measures, mu and nu, with a density f mu and f nu with respect to the Lebesgue measure. Then the convolution again has a density, and its density can compute like this here. Well, t is the same left and right. S has to be somewhere, and yeah, f nu then has to be like that. That's the sum here plus the nu. Yeah, so like this. So s plus t minus s equals t, and that's the value here also, and I integrate over s. That's the point. For example, if I have two normal distributions and I want to compute their convolution, I claim, well, if I do this, I have a density, which is then the density of n, and what happens? Mu1 plus mu2, sigma 1 squared plus sigma 2 squared. So I just have to add up the expectations and the variances. In order to see this, we're using this formula here. And f mu is the density of the normal distribution, which comes with 1 over square root of 2p sigma 1 squared and 2p sigma 2 squared. So I have this here for the prefactor. And in the integral, I have the 2e to the minus somethings. And here s plus t minus s equals t. So I have y here. Y plus x minus y equals x, which is exactly the value I want to compute now. Okay, I have to integrate over y, which is not so easy at first glance, but it's doable. I have a y square here. I have a 2y times mu1 here. I have x's here, and I have mu here, also the power of 2. So I can compute and compute and compute. For the y, I can write it differently, like this here. E to the minus, well, this here, minus this here. And now you realize wait, some y's are missing here, I think. Yeah, no, here's a y. Here's the only y, actually. I have to integrate over this. And I can do this because all the rest goes as a prefactor in front of the integral. And when you do the maths correctly, you end up having this distribution here, 1 over square root 2p sigma square. And what stays? X minus mu divided by 2 sigma squares here. And the rest all goes away. So this here is the density of the convolution, which is then, again, the density of here f n mu1 sigma 1 square convoluted with f n mu2 sigma 2 square. And that's how you can compute that the convolution of two normal distributions is, again, a normal distribution. Okay, that's it for today. Next video is the last one, which is dealing with the distribution of random processes. See you then.